Hello everyone. So today we will talk about power, energy conservation, momentum conservation, and their influence on collisions. Okay, so in the last class we have talked about energy and work done. We are now familiar with the thing that energy transfer is actually the work done. How, like, if there are two objects A and B, and the first object wants to change the state of second object, that is my B. So in that case, what he has to do, or it has to do, it has to transfer some of its energy to B object, right? How it will transfer the energy? By means of imparting force on B, right? So this energy transfer we take as work done. So work done of A on B. So we say the thing like this, and we have seen that work done is actually a scalar quantity which is F dot R, where F is the force and R is the displacement. Before we go into power, we must know some more things about the work done, force and displacement. How, like, okay, so this we can write as F R cos theta, whereas F and R mods are the values and theta is the angle between F and R. So if there is an object and I have given the force somehow, and because of this force the object has gone in this way, so I can see here there is a certain angle between the force imparted on the object and the displacement, uh, like, which has occurred due to the object. So this is the work done. Now in this case we can see this force in this formula has been taken as constant force. That means the value of the force is not changing in this case, but there are some cases where the value of force can change as well. So in those cases, how we will calculate the work done? So in those cases what we do, we see that, let's say, in some scenario the amount of force is increasing like this with displacement. So force in this way, displacement that way. So as the displacement is happening, we have seen that our force is also increasing. Like how? Like in the case of spring. So we have seen that for spring F is minus kx. So this force, so the spring is fixed here and here is the end, and we want to compress the spring. So the force is giving us this amount of the spring is giving us this amount of force, but we have to give the same amount of force but in opposite direction. So we say that we are giving F equal to kx, but you can see here that the force itself is dependent on x. So as the x is changing, as we compress the spring, the value of F is also changing with it. So in those cases the force is not constant. So in this case, how we will find out the work done? What we will do, we will take a small portion of displacement. Okay, so we will say like this, ki for very little, for infinitesimal displacement dx. So I told you dx is actually a very small x. So when you take something so small that is like the smaller than you can think of. Okay, so in that case we use d. This is some kind of differential what you say displacement. So it is a small displacement. For the small displacement, this variation of f, that is the change of f, will be also very small, right? So we can take that small f as a constant. We cannot take the whole thing like from here to here, the total force we cannot take constant because we can see it's changing. But if you take a very small quantity, so for this location we can say that df is almost constant, it is not changing. So in that case we can say to do this much of displacement I have to do dw of work. So in my case I can always write this is equal to f dot dx. Okay, now I know f is a function of x and we write the function as this. So f is a function of x, that means x f is dependent on x, right? F varies with the value of x. So what we can write, I will also write here that f is a function of x. This is not multiplication, okay, don't make mistake. This is a function that shows the dependence on some variable. So dw is the small quantity work which is required to or like to have a displacement dx. Okay, so now if we take those small portions all together and add them all, then only we will get the total work done. So what we will do, we will integrate it. Let's say I am going to find the work done from here a point to a b point. So in that case what I will do, I will integrate from a to b. So there will be integration as well. So just like I have found out the before only the potential energy, and you have seen this kind of integration there. So we can say that w is equal to integration f dx. Okay, or you can better say this integration will happen only when force is a function of x. So the a dx and you have to take the limit, like from which point to which point you are like counting the force value, or it's where you can better say this limits are basically x ka value. So this is displacement 1 to displacement 2. So this is the thing, like this is how we have to find out work done when we have something like when the force is variable. One more interesting thing is here, we will also talk about it, that is how to find out work done from a graph. Let's say we have a curvature like this. So I have something like this, and we have something like this as well. So you can see that in this case let me change the color. Okay, so in this case, if say this x axis is displacement, whereas my this axis is force, and I have to find out this is the 0 point, and let's say this is r equal to 10 meter, whereas the f value, this is 0 and this is the f value is say 10 Newton, and I have to find out work done. So as we know that work done for any general case is f into tx for any general case. Now if f is my what you say, f is my constant, so it will come out and it will be simple formula, that is f equal to f into x. But if it is not a constant, then we will be sticking to this formula. Now if you go into the integration part, you will see that this integration is nothing but the area under the curve. So any kind of integration is always the area under the curve. Okay, so we have seen here that if we have like say uh, f and x, so this is the curvature and the area under the curve will be nothing but the work done itself. So this area under the curve will be work done. So if we just find out what is the area under the curve, then it will be very much easy for us to find out the work done. So for that, what we will do, we will create here an imaginary line. So we have one triangle and one rectangle, and this will be also given somehow. So let's say it is given something like 5 or so, 5 meter. So in your entrance exams also you will find some this kind of numericals. So the total area or the work done, you can say the area of this rectangle. So the area of rectangle plus area of triangle. So if we just decode this thing, so you can simply write this is nothing but your length into breadth plus half into, this is also the interval, this interval is also 10 minus 5, that is 5 only. So I'm writing the whole so that there is no confusion, into 10 the height. So ultimately you can get the total work done as your 50 plus 25, that is 75. So you can easily get these things. So 75, and this is joule because we are talking with SI unit. So this is how we can also find out the work done. Now talking about power. So power is basically very much linked with our work done. Power is nothing but the rate of work done. So power is rate of work done or rate of energy transferred with respect to time. Why with respect to time? Because the rate we are talking about is with respect to time. So what we can write that power is nothing but the rate of change of work done. So in unit time, how much work done is happening, that is our power. So if in the case like when your work done is constant, so you can write this thing. So when your work done is constant, you can simply write this thing, that is you are having a uniform work done. But in the case when your work done is not, like say if W is not constant, so in that case what you will write, you can write P is equal to dW by dt. That is in that case, like say if you have work done here and time here, and you see that the energy is transferred like in the first case it is slow, but later on the rate is increasing, the like energy is increasing. So in that case you will give something like this curve, and you see that here the W is not constant, right? So in this kind of graph W is constant, and you can use directly this formula. But in case of the graph above, you cannot use that formula. So we have to take a very small portion and we have to talk about that only. Okay, so in this case we can see that work done is our dW by dt. Also we can get some other formulas like we know also that this W is equal to F and dx, right? Or that we know that the dW equal to F dx in case of variable work. or like in general case also you can use this formula. So if we substitute this thing, so we can write d dt of f dot dx. Now if our f is constant, so if f is constant, so it will be given in the question itself. So if it is constant, so it will be given in the question itself. Okay, you don't have to bother about it. So f will come out and we will get a dx dt, and that is how we will get a formula, that is f dot v, because we know dx dt is nothing but our what you say, nothing but our velocity. So if we use vector terminology here and it is dot product, so we will get something like this. So though p is a scalar quantity because it is merely a value, so we can write now our formula that f equal to f dot v also, provided when f is constant, f value is not changing. Other way, normally generally p is equal to w by t, you can say generally. Okay, so once you get the answer for w, you just divide it by the time taken for that transfer of the energy, and you can get the power easily. The unit for the power is watt. Basically we use watt, but some more things are there, like if you see some big vehicles, supercar, super bike, you will find something like horsepower. So 1 horsepower, it is written as directly HP. Okay, so I will write HP, 1 horsepower is 746 watt. So basically when we have mechanical work done, like your engine is transferring its combustion and like energy, like mechanical energy into kinetic energy, which is driving your car, in that case we use this horsepower. But in basically, like say we are talking about electrical circuit, and we know that the heat dissipated by any electrical circuit is I square RT. I think you have already read it in your previous class. So in those cases also we can write the same formula, that is I square RT by T, that is I square R. But in those cases the P formula is same, okay, that is work by time, but the unit we basically use is 1 kilowatt. So you use kilowatt, okay, hour. So basically what is the definition of this 1 kilowatt hour? So if 100 watt bulb, if it is like turned on, or it is like blinking, if 100 watt bulb is what you say, is illuminating for 10 hours, then the energy or the power, output, we say 1 kilowatt hour, or in normal sense we say BOT. Okay, 1 BOT, 1 B dot O dot T, also we say this BOT or 1 kilowatt hour. These are the same things. So sometime we say 1 BOT. Basically in your home you will find people used to say unit, 5 unit current has been done, like 5 unit power has been done, 6 unit power has been done, like basically in our house we use unit, but that is actually 1 BOT or 1 kilowatt hour. Okay, so these are the unit for power. Now as we have learned this formula, that P equal to F dot V, so if you have like this kind of graph, And then if you have something like this, keep the process is like this, and in this case let's say your v is f is given and the velocity is given, and you have this limits also where there is a certain change is occurring, so this v value is also given, let's say. So in those cases, so let's say this is v1. So in those cases the area under the graph is nothing but your power itself. So you can directly tell that in these cases this whole area under the graph will be nothing but your power. So you just find out the area by geometry under the graph and you will get the power. So if it is given force and displacement, then it is work, as I have told in my last topic, this one. And if this is force and velocity, then it is nothing but your power. So this is it, all about power and energy. Basically this much will be helpful for us to do numericals. And now let's talk about something interesting, that is momentum conservation. Now there is a very interesting thing you know this thing that if we have a cannon, I'm very bad at drawing, but still, if we have a barrel cannon, so this is a cannon, let's say, and then let's say we have a ball in it, like the bomb in it. So when the cannonball released from the when the cannonball is released from the cannon, what happens? The cannonball goes this direction, and you see that there is a big jerk in opposite direction. So the cannon comes back side, right? So why this happens? Now let us talk about this. So you can see that when the cannonball is here, what is happening? The velocity of the cannon and the cannonball is 0, right? But when the cannonball is going this side, so they have certain velocity. So let's say this cannonball is moving with velocity v2, the cannon is going back with a velocity, and I don't know it's going back or not, I will see that. So it's, if it is velocity v1, okay, or we can say this is c and this is b for our better understanding. So you remember the momentum conservation, and I told you that if the system is isolated and if there is no other influences in the system, the momentum is always conserved within the system. So momentum conservation will tell us that the initial momentum will be same as the final momentum, right? So in this case we can see the initial momentum was 0, because let's say the mass of the cannon is m, mass of the ball is small m. So in that case m is not 0, but the velocity before the ball being fired, the velocity was 0, so initial was 0, and the final was m v b, that is for cannonball, plus big M and vc. Now I'm not taking, I don't know, let's say I don't know like what is the direction of the velocities, but this equation will give me that the vc is my minus mvb by m. So you can see here the velocity of the cannon is in the opposite direction, because there is a minus sign with regarding with the velocity of our cannonball, And one more thing is noticeable, that this big M is in the denominator. So what do you want, like if you are firing a cannonball, and do you want your cannon to go in the opposite direction with high speed and injured those who are firing? Obviously not. So what we do, what like people used to do in earlier like cases, you see that they used to jam this like somehow they used to either jam the wheels, or they used like heavy cannon. Okay, so they used to add a lot of weight to the cannon, so that this aim is like bigger, and that's why this what you say, this fraction will be smaller. So the VC, that is the recoil velocity, so this thing is called recoil velocity. So this recoil velocity will be less in that case, and the people who are firing will not have any like risk of injury. So this is basically we will be talking about the momentum conservation. But what is our today's motive is to just to start the topic of collision. So what is collision? Collision means what you say, when two or more objects collide with each other. So there may be many cases, and based on their what you say, energy conservation, we have categorized them in two ways. So collision is actually categorized in two different sections. One is elastic collision. So one is elastic and one is inelastic collision. Now what is elastic and what is inelastic collisions? Now elastic collisions means where there will be kinetic energy, and the initial kinetic energy and final kinetic energy will be same. I'm not talking about conservation of energy. Okay, obviously energy will be conserved in both of these cases if you take the whole system, but in this case kinetic energy initial and kinetic energy final will not be same. Why? Because this kinetic energy initial will somehow be converted into some another energy, let's say potential energy. Now how? Let's say in this case we see this is the most practical case, that is the inelastic collision. When we have a ball and it is colliding with another ball, what will happen? When this ball will collide with this ball, now this ball is not rigid, so nothing in this world is perfectly rigid, right? So as a result, what will happen? This ball will squeeze, so the shape of this ball will squeeze little bit, so it will become oval, and this first ball will also become little much of oval. So what is happening? So this incoming energy is actually deforming the shape of another object. As a result, some of the kinetic energy is being converted into potential energy. Why? Because it is doing work, and what it is doing, it is deforming the object. Also, let's say if you throw two snowballs, and when the snowballs collide with each other, what happens? They become fragmented. So in that case also they are like all the energies are converted somehow, and it distributes in like the what you say, the ice crystals, okay, in order to deform them or to break them. So those are the practical examples of inelastic collisions. We will be talking about this inelastic collisions and elastic collisions in our next class as well. And talking about momentum conservation, so one more thing, in elastic collisions generally it is not practical, because we don't have such what you say, perfectly rigid body. So rigid means when we cannot deform anything. So the things which are not deformable, they are called rigid. And because in our real world everything is made of bonds, right? Like covalent bond or some kind of bond, and these bonds are generally not rigid, so they are somehow what you say they are somehow collapsible or extensible, so we can deform them, we can change the distance between the bonds. That's why nothing is perfectly rigid in the world. But elastic collision generally happens like it, we cannot get exactly elastic collisions, but it's partially elastic collisions, and we get it in billiard boards. When we play billiard board and we see that a slight hit in one of the ball, and that ball is rolling and it is colliding with another ball, and that ball is also rolling, and only in those kind of scenario we can get an approximation towards elastic collisions. Talking about momentum conservation, if one more case happens here, that like that momentum, this initial and final, this momentum are generally they are vector quantities, so we can always talk as vector quantities here. So if you see somewhere that let's say this is one object, it was going, it is now like somehow it is brusted, and then one portion of it is going in this way, one portion of it is in going that way, and they are making an angle, let's say theta 1 and theta 2. So this was the total portion, let's say a plus b, and the a portion is going that way after the blast, and b portion is going that way. So how I will find out the velocities and everything? So let's say the total velocity is v, this one is going with velocity v1, this one is going with velocity v2. So in this case what I have to do, because these velocities are vector quantities, so I have to take them all in one single line. So if I take this line as this axis, let's say this axis x axis, if I take this all as in this axis, and if I take another axis, that is my y-axis here, so in one line I will calculate the things. Okay, like so what I will do, I will write that in x-axis, so in along x-axis my mass, so this a b, these are the mass, let's say mass, this is also mass, this is also mass. Okay, I'm not writing MBMA, I'm just talking about AB. So we can write that A plus B V, so that was the initial, and finally what I am getting A V1, but I have to take the velocity along x-axis, so this is cos theta 1 plus B V2 and cos theta 2. So what basically I'm doing, I'm taking the projection of V2 along x-axis, projection of V1 along x-axis. So this is my one along x-axis. Okay, so this is along x-axis, don't think that this is multiplication, I better not write it. So this is along x-axis, and along y-axis what I can write, I can write that V1 sine theta 1, so a v1 sine theta 1 is equal to a v2, sorry b v2 sine theta 2. And using our this two equations we can easily solve for our concerned value. Okay, if like some values are given, so we can find out other values. So you have to just remember one thing clearly, that momentum is a vector quantity, and whenever we are dealing with vector quantity we must take them along x and y axis. You must, okay, if it is like say your force, whether it is your momentum, whether it is your velocity, whenever you are like you have to deal with those kind of vector quantities, you must take x and y axis and take the components along that axis, that those two axes, and then you equate. Okay, but in case of what you say energy, we are not going to do that. Okay, so in case of energy we can directly, because energy is a scalar quantity, and in our next class we will be doing so. So this much is the class for today, and I hope you watch this carefully, because this class is very important. It will help to build your concept, and I will see you in my next class. Thank you for the class.